When sizing isolated ground circuits and feeders, the best approach involves several key steps. Firstly, determine the connected load. Calculate the combined load of all devices connected to the isolated ground system. Secondly, apply a demand factor. Multiply the connected load by a demand factor of 0.85 or 0.90, depending on the type of load, whether it's continuous or intermittent. Thirdly, size the branch circuits. Determine the ampacity of the branch circuits based on the calculated load and the maximum allowable voltage drop. The National Electrical Code, or NEC, generally requires branch circuits to be sized for 125% of the calculated load. Fourthly, size the feeders. Determine the ampacity of the feeder supplying the isolated ground system based on the sum of the branch circuit loads. The feeder should also be sized for 125% of the calculated load. Fifthly, consider voltage drop. Ensure that the voltage drop between the source and the isolated ground system is within acceptable limits. This can be calculated using Ohm's law, where voltage drop equals load times resistance times distance. Now, regarding daisy chaining the isolated ground conductor, yes, daisy chaining the IG conductor is permitted. However, it's important to ensure that the IG conductor is sized correctly for the full load of all devices connected to the isolated ground system. Additionally, all connections must be made properly and securely. Finally, the connections must be protected from physical damage and moisture. Also, there are additional considerations to keep in mind. The isolated ground system must be isolated from the primary electrical system using an isolation transformer. Also, the IG conductor must be grounded at the isolation transformer. It is recommended to have the isolated ground system inspected by a qualified electrician to ensure compliance with all applicable codes and standards. The National Electrical Code addresses isolated grounding in Section 250.96b, which pertains to the bonding of metal raceways and enclosures containing isolated ground conductors. This section clarifies that where isolated ground conductors are installed, the metal raceways and enclosures containing these conductors must be bonded to the grounding electrode system. This requirement ensures that even with an isolated ground, the overall safety and grounding integrity of the electrical system are maintained. Article 250 provides comprehensive guidelines for grounding and bonding to ensure electrical safety. When dealing with sensitive electronic equipment, isolated grounding is often implemented to minimize electrical noise and interference. This involves creating a separate grounding path for the equipment that is isolated from the regular equipment grounding system. The purpose is to prevent stray currents and electromagnetic interference from affecting the performance of the sensitive equipment. However, it's important to note that an isolated ground is still connected to the main grounding electrode system at the service entrance to maintain safety and prevent voltage differences. The NEC provides specific guidelines for installing and using isolated grounding systems. Section 250.146 covers the requirements for connecting the equipment grounding conductor of a branch circuit supplying sensitive electronic equipment to an isolated ground receptacle. It states that the isolated ground receptacle must have a connection to an insulated equipment grounding conductor run with the branch circuit conductors. This insulated equipment grounding conductor is allowed to pass through one or more panel boards without being connected to the panel board grounding bus. The isolated equipment grounding conductor must terminate at the grounding bus of the derived system or service where the branch circuit originates. One important rule is that the isolated ground conductor must not be connected to the metal raceway or enclosure containing the circuit conductors. This isolation helps prevent unwanted currents from flowing through the grounding system. The NEC also emphasizes the importance of proper identification of isolated ground conductors and receptacles. Isolated ground receptacles are typically orange in color and have a triangle symbol to indicate that they are part of an isolated grounding system. This helps prevent accidental connection to the regular equipment grounding system. In addition to the NEC, other standards and guidelines may apply to isolated grounding systems depending on the specific application and location. These may include industry-specific standards or local electrical codes. When designing and installing an isolated grounding system, it's essential to follow all applicable codes and standards to ensure safety and effectiveness. A qualified electrician with experience in isolated grounding systems should be consulted to ensure that the system is properly designed and installed. Proper grounding and bonding are critical for electrical safety and to prevent electrical shock hazards. The NEC provides detailed requirements for grounding and bonding to ensure that electrical systems are installed safely and effectively. Grounding and bonding help to create a low impedance path for fault current, which allows overcurrent protection devices to quickly trip and clear the fault. This reduces the risk of electrical shock and equipment damage. Grounding involves connecting the non-current carrying metal parts of an electrical system to the earth. This provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to operate. Bonding involves connecting the non-current carrying metal parts of an electrical system together to create an electrically conductive path. This helps to equalize voltage potentials and reduce the risk of electrical shock. The NEC specifies the types of grounding and bonding conductors that must be used in electrical systems. These conductors must be sized appropriately to carry the available fault current. The NEC also specifies the methods for connecting grounding and bonding conductors to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete-encased electrode. It's important to note that grounding and bonding requirements can vary depending on the type of electrical system and the location. A qualified electrician should be consulted to ensure that the grounding and bonding system is properly designed and installed. In addition to safety, proper grounding and bonding can also improve the performance of electrical equipment. By reducing electrical noise and interference, grounding and bonding can help to ensure that sensitive electronic equipment operates reliably. The demand factor is a crucial element in electrical load calculations, particularly when sizing feeders and service entrances for buildings. It accounts for the fact that not all electrical loads within a building will operate at their maximum capacity simultaneously. By applying a demand factor, engineers and electricians can more accurately determine the actual load requirements, which can lead to cost savings and improve system efficiency. The demand factor is typically expressed as a percentage or a decimal value less than 1.0. It represents the ratio of the maximum demand of a system to the total connected load. For example, a demand factor of 0.8 means that the maximum demand is expected to be 80% of the total connected load. The NEC provides demand factors for various types of loads such as lighting, appliances, motors, and HVAC equipment. These demand factors are based on statistical data and industry experience. However, it's important to note that the NEC demand factors are general guidelines and may not be appropriate for all situations. In some cases, it may be necessary to use different demand factors based on the specific characteristics of the load and the building. To determine the appropriate demand factor for a particular load, it's important to consider the following factors: the type of load, the usage patterns, the diversity of the load, and the size of the load. For example, lighting loads in an office building may have a higher demand factor than lighting loads in a warehouse because office buildings typically have more consistent lighting usage. Similarly, motor loads may have a lower demand factor than lighting loads because motors are often used intermittently. The demand factor is applied to the connected load to calculate the maximum demand, which is then used to size the feeder or service entrance conductors. For example, if a building has a connected load of 100 amps and the demand factor of 0.75, the maximum demand would be 75 amps. This means that the feeder or service entrance conductors would need to be sized to carry at least 75 amps. It's important to note that the demand factor is not the same as the load factor. The load factor is the ratio of the average load over a period of time to the peak load during that period. The demand factor is used for sizing conductors and overcurrent protection devices, while the load factor is used for energy management and cost analysis. In addition to the NEC, other standards and guidelines may provide demand factors for specific types of loads. These may include industry-specific standards or local electrical codes. When calculating electrical loads, it's essential to use the appropriate demand factors to ensure that the electrical system is properly sized and operates efficiently. A qualified electrical engineer or electrician should be consulted to determine the appropriate demand factors for a particular application. Voltage drop is an important consideration in electrical system design because it can affect the performance and efficiency of electrical equipment. Voltage drop occurs when the voltage at the end of a conductor is less than the voltage at the source. This is due to the resistance of the conductor, which causes a voltage drop as current flows through it. Excessive voltage drop can cause a variety of problems, including reduced equipment performance, increased energy consumption, and premature equipment failure. The NEC provides guidelines for voltage drop in branch circuits and feeders. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and the voltage drop in a feeder should not exceed 5%. These voltage drop limits are based on the type of load and the length of the conductor. To calculate voltage drop, you can use Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance. The formula for voltage drop is voltage drop equals current times resistance. The current is the amount of current flowing through the conductor, and the resistance is the resistance of the conductor per unit length. The resistance of a conductor depends on its material size and temperature. Copper and aluminum are the most common conductor materials used in electrical systems. Copper has a lower resistance than aluminum, so it is often preferred for long runs or high current applications. The size of a conductor is typically expressed in terms of its cross-sectional area, which is measured in circular mils of square millimeters. Larger conductors have lower resistance than smaller conductors. The temperature of a conductor also affects its resistance. As the temperature increases, the resistance also increases. To minimize voltage drop, it's important to use conductors that are large enough to carry the load and that have low resistance. You can also reduce voltage drop by shortening the length of the conductor or by using multiple conductors in parallel. When calculating voltage drop, it's important to consider the total length of the conductor, including both the supply and return paths. You should also consider the voltage drop in any connectors or splices in the circuit. Voltage drop can also be affected by the power factor of the load. Power factor is a measure of how effectively electrical power is being used. A low power factor can increase voltage drop and reduce the efficiency of the electrical system. To improve power factor, you can use power factor correction capacitors. In addition to the NEC, other standards and guidelines may provide voltage drop limits for specific types of loads. These may include industry-specific standards or local electrical codes. When designing an electrical system, it's essential to calculate voltage drop to ensure that the equipment will operate properly and efficiently. A qualified electrical engineer or electrician should be consulted to perform voltage drop calculations and to select the appropriate conductors for the application. The ampacity of a conductor is the maximum amount of current that it can carry continuously without exceeding its temperature rating. The ampacity of a conductor depends on its material size, insulation type, and installation conditions. The NEC provides ampacity tables for various types of conductors in different installation conditions. These ampacity tables are based on extensive testing and are designed to ensure that conductors are used safely and effectively. The ampacity of a conductor is typically expressed in amps. The ampacity of a conductor is determined by its ability to dissipate heat. When current flows through a conductor, it generates heat due to the resistance of the conductor. If the heat is not dissipated quickly enough, the temperature of the conductor will rise. If the temperature of the conductor exceeds its temperature rating, the insulation can melt or degrade, which can lead to a short circuit or fire. The NEC specifies the maximum allowable temperature for various types of conductor insulation. These temperature ratings are based on the chemical and physical properties of the insulation material. To ensure that conductors are used safely, it's important to select conductors with an ampacity that is sufficient to carry the load. The NEC requires that conductors be sized to carry at least 125% of the continuous load. This provides a safety margin to account for variations in load and ambient temperature. The ampacity of a conductor can be affected by the installation conditions. For example, conductors that are installed in conduit or cable trays may have a lower ampacity than conductors that are installed in free air. This is because the conduit or cable tray can restrict the flow of air around the conductor, which reduces its ability to dissipate heat. The NEC provides adjustment factors for ampacity based on the installation conditions. These adjustment factors are used to reduce the ampacity of a conductor when it is installed in a restricted environment. In addition to the NEC, other standards and guidelines may provide ampacity ratings for specific types of conductors. These may include industry-specific standards or local electrical codes. When selecting conductors for an electrical system, it's essential to consider the ampacity of the conductors and the installation conditions. A qualified electrical engineer or electrician should be consulted to select the appropriate conductors for the application. The continuous load is the load that is expected to operate continuously for 3 hours or more. The NEC requires that conductors be sized to carry at least 125% of the continuous load. This is to prevent overheating of the conductors and to ensure that they can operate safely and reliably. To determine the continuous load, you need to identify all of the loads that are expected to operate continuously for 3 hours or more. This may include lighting, HVAC equipment, and other appliances. Once you have identified the continuous loads, you need to calculate the total current that they will draw. This can be done by using the nameplate ratings of the equipment or by measuring the current with an ammeter. After you have calculated the total continuous current, you need to multiply it by 1.25 to determine the minimum ampacity of the conductors. For example, if the total continuous current is 20 amps, the minimum ampacity of the conductors would be 25 amps. It's important to note that the NEC also requires that overcurrent protection devices be sized to protect the conductors. The overcurrent protection device should be sized to protect the conductors from overload and short-circuit conditions. The overcurrent protection device should not be larger than the ampacity of the conductors. In addition to the NEC, other standards and guidelines may provide requirements for continuous loads. These may include industry-specific standards or local electrical codes. When designing an electrical system, it's essential to consider the continuous loads and to select conductors and overcurrent protection devices that are properly sized to handle the load. A qualified electrical engineer or electrician should be consulted to perform load calculations and to select the appropriate conductors and overcurrent protection devices for the application. Proper grounding and bonding are essential for electrical safety and to prevent electrical shock hazards. Grounding and bonding help to create a low impedance path for fault currents, which allows overcurrent protection devices to quickly trip and clear the fault. This reduces the risk of electrical shock and equipment damage. Grounding involves connecting the non-current carrying metal parts of an electrical system to the earth. This provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to operate. Bonding involves connecting the non-current carrying metal parts of an electrical system together to create an electrically conductive path. This helps to equalize voltage potentials and reduce the risk of electrical shock. The NEC specifies the types of grounding and bonding conductors that must be used in electrical systems. These conductors must be sized appropriately to carry the available fault current. The NEC also specifies the methods for connecting grounding and bonding conductors to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. It's important to note that grounding and bonding requirements can vary depending on the type of electrical system and the location. A qualified electrician should be consulted to ensure that the grounding and bonding system is properly designed and installed. In addition to safety, proper grounding and bonding can also improve the performance of electrical equipment. By reducing electrical noise and interference, grounding and bonding can help to ensure that sensitive electronic equipment operates reliably. An isolation transformer is a transformer used to transfer electrical power from a source of alternating current power to some equipment or device while isolating the power device from the power source. usually for safety reasons. Isolation transformers provide galvanic isolation and are used to protect against electric shock, to suppress electrical noise in sensitive devices, or to transfer power between circuits which are not supposed to be connected. An isolation transformer's main purpose is to isolate a device from the power source. This is achieved by having separate primary and secondary windings that are not electrically connected. The energy is transferred through electromagnetic induction. This isolation helps to prevent ground loops and reduces the risk of electric shock. Isolation transformers are designed with 11 ratio between the primary and secondary windings. This means that the voltage on the secondary side is the same as the voltage in the primary side. However, the transformer can also be designed with different voltage ratios to step up or step down the voltage. Isolation transformers are used in a variety of applications, including medical equipment, audio equipment, and industrial control systems. In medical equipment, isolation transformers are used to protect patients from electric shock. In audio equipment, they are used to reduce noise and interference. In industrial control systems, they are used to isolate sensitive control circuits from the power line. When selecting an isolation transformer, it's important to consider the voltage, current, and power requirements of the equipment being powered. You should also consider the isolation voltage ratio of the transformer, which is the maximum voltage that the transformer can withstand between the primary and secondary windings. A qualified electrical engineer or electrician should be consulted to select the appropriate isolation transformer for the application. In addition to safety, isolation transformers can also improve the performance of electrical equipment. By reducing electrical noise and interference, isolation transformers can help to ensure that sensitive electronic equipment operates reliably. The size of the equipment grounding conductor, or EG, is crucial for safety in electrical systems. It provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly trip and clear the fault. This minimizes the risk of electrical shock and equipment damage. The NEC provides detailed guidelines for sizing EGC based on the size of the overcurrent protection device protecting the circuit. Section 250.122 in the NEC is the primary reference for determining the minimum size of EGC. The size of the EGC is typically based on the ampere rating of the overcurrent protection device protecting the circuit conductors. For example, if a circuit is protected by a 20 amp circuit breaker, the EGC must be at least a 12 American wire gauge copper conductor according to NEC Table 250.122. It's important to note that the EGC must be sized large enough to safely carry the available fault current. If the EGC is too small, it can overheat and potentially cause a fire or electrical shock hazard. In some cases, the EGC may need to be larger than the minimum size specified in the NEC. This may be necessary if the circuit has a long run length or if the available fault current is high. The NEC also provides requirements for the type of conductor used for the EGC. The EGC must be made of copper, aluminum, or other approved material. The EGC must also be protected from physical damage. In addition to the NEC, other standards and guidelines may provide requirements for the size and type of EGC. These may include industry-specific standards or local electrical codes. When designing an electrical system, it's essential to properly size the EGC to ensure safety and prevent electrical shock hazards. A qualified electrical engineer or electrician should be consulted to determine the appropriate size and type of EGC for the application. It's important to understand the difference between the EGC and the grounded conductor, also known as the neutral conductor. The EGC is used to provide a path for fault currents, while the grounded conductor is used to carry the normal unbalanced current in a circuit. The EGC is typically connected to the equipment enclosures and other metal parts of the electrical system, while the grounded conductor is connected to the neutral point of the power source. The equipment grounding conductor serves a critical role in electrical safety by providing a low impedance path for fault current to return to the source. This path facilitates the rapid operation of overcurrent protection devices, such as circuit breakers or fuses, in the event of a ground fault. By quickly clearing the fault, The EGC minimizes the duration of potentially dangerous voltage on metal equipment enclosures, reducing the risk of electric shock to personnel. The sizing of the EGC is determined by the ampere rating of the overcurrent protection device protecting the circuit. The NEC provides tables, such as Table 250.122, that specify the minimum size of the EGC based on the rating of the overcurrent device. It's essential to consult these tables to ensure that the EGC is adequately sized to handle the available fault current. The EGC must be installed in accordance with NEC requirements, including proper termination and protection from physical damage. It should be connected to all metal enclosures, raceways, and other non-current carrying metal parts of the electrical system. This ensures that a continuous, low-impedance path is maintained throughout the system. In addition to providing a path for fault current, the EGC also helps to minimize electrical noise and interference. By providing a low-impedance path to ground, the EGC helps to shunt away unwanted currents and voltages that can interfere with the operation of sensitive electronic equipment. The EGC plays a vital role in maintaining the overall safety and reliability of electrical systems. Proper installation and maintenance of the EGC are essential to ensure that it can effectively perform its intended function. The isolated ground conductor, or IG, is a special type of grounding conductor used in electrical systems to minimize electrical noise and interference. It is typically used in sensitive electronic equipment, such as computers, audio equipment, and medical devices, where even small amounts of electrical noise can disrupt performance. The IGC is similar to the EGC, but it is isolated from the normal equipment grounding system. This isolation helps to prevent unwanted currents from flowing through the grounding system and interfering with the operation of sensitive equipment. The NEC provides guidelines for the installation of IGC in Section 250.146. The IGC must be an insulated conductor and must be run with the circuit conductors. The IGC must terminate at the grounding bus of the derived system or service where the branch circuit originates. The IGC must not be connected to the metal raceway or enclosure containing the circuit conductors. The IGC must be identified by orange color coding or by other means acceptable to the authority having jurisdiction. The use of an IGC can significantly reduce electrical noise and interference in sensitive electronic equipment. However, it is important to follow the NEC guidelines for installation to ensure that the IGC is properly installed and does not create a safety hazard. In addition to the NEC, other standards and guidelines may provide requirements for the installation of IGC. These may include industry-specific standards or local electrical codes. When designing an electrical system for sensitive electronic equipment, it is essential to consider the use of an IGC to minimize electrical noise and interference. A qualified electrical engineer or electrician should be consulted to determine the appropriate grounding system for the application. The isolated ground receptacle is a special type of electrical receptacle that is designed to minimize electrical noise and interference. It is typically used in sensitive electronic equipment, such as computers, audio equipment, and medical devices, where even small amounts of electrical noise can disrupt performance. The isolated ground receptacle is similar to a standard electrical receptacle, but it has an isolated grounding terminal. This terminal is connected to an insulated grounding conductor that is run back to the grounding bus of the derived system or service where the branch circuit originates. The isolated grounding terminal is not connected to the metal box or other metal parts of the receptacle. This isolation helps to prevent unwanted currents from flowing through the grounding system and interfering with the operation of sensitive equipment. The NEC provides guidelines for the installation of isolated ground receptacles in Section 250.146. The isolated ground receptacle must be identified by an orange triangle on its face. The insulated grounding conductor must be run with the circuit conductors. The insulated grounding conductor must terminate at the grounding bus of the derived system or service where the branch circuit originates. The insulated grounding conductor must not be connected to the metal raceway or enclosure containing the circuit conductors. The use of an isolated ground receptacle can significantly reduce electrical noise and interference in sensitive electronic equipment. However, it is important to follow the NEC guidelines for installation to ensure that the isolated ground receptacle is properly installed and does not create a safety hazard. In addition to the NEC, other standards and guidelines may provide requirements for the installation of isolated ground receptacles. These may include industry-specific standards or local electrical codes. When designing an electrical system for sensitive electronic equipment, it is essential to consider the use of isolated ground receptacles to minimize electrical noise and interference. A qualified electrical engineer or electrician should be consulted to determine the appropriate grounding system for the application.